All right, shall we? Cool. This is Conway's Game of Life. Most of you are probably familiar with it. It's an unusual zero-player game where patterns change over time, a bit like life evolving, with cells living and dying, following very simple rules. Some of you have probably actually written the code that implements this for one reason or another, and it normally looks a bit like this. 3 nested loops going over the board, evaluating the cells one at a time, counting the neighbors around them, setting the new state, repeating forever. Now, a few months ago, this weird idea popped into my head, and I couldn't shake it off. Could you implement it like this instead? Could you implement the game of life with just the regex? And if you can, then what does that mean for our understanding of what regular expressions can do? First of all, though, hi, my name is Daniel, and I work at Indeed Flex. We are a flexible staffing company based in London. As you probably noticed, though, I'm not originally from London. I come from Argentina, so in case you were wondering, that's the accent. And now that we got that out of the way, let's go back to this weird question that I had. Can you implement the game of life with just the regex? And at first, this question sounds nonsensical, right? I mean, regular expressions are a pattern matching tool. How would you ever be able to drive behavior with them? You know, we need to look through all of these cells, count the neighbors, make some decisions. How could you ever do that? Some of you might also be asking, Daniel, but why? And if you're asking that question, you might not enjoy the rest of this talk. You might be a bit too sane for this. But for the rest of you, wondering whether this is possible, the answer is yes, kinda, there's some caveats. But I think the solution is quite interesting, and I think the implications of it are quite interesting, which is why I like to share this with you. Now, in order for the approach to make sense, I won't be able to just jump straight to the answer. I'm gonna have to walk you through more or less the same steps that I had to take, and that includes some dead ends and some intermediate solutions. What I would recommend is that you try to stay ahead of me and think of how you would solve these problems yourself if you had them. It's gonna make the talk a lot more fun. And also, there's gonna be some code on the screen that flies a little bit fast, but I'm gonna share a link to a repo at the end where you can see all of the code in detail. It's slower if you want later. So, first of all, let's look at the game of life and what the rules are. We have a 2-dimensional board of cells. Each cell can be either alive or dead. Let's think of this as 1 and 0. And this board evolves over generations. On each new generation, each cell will be alive or dead based on how many neighbors it had in the previous generation. If you have too few, it dies. And if you have too many, it dies. And if it was dead but had exactly 3 neighbors, it spawns into new life. And that's what you see happening up there in that board. Now, those rules reduce to this simple expression. You're gonna have to trust me here. In the next generation, you're alive if and only if you now have 3 neighbors, or if you have 2 and are already alive. Or put another way, these are the transitions you could have. This guy is gonna die of loneliness because he only has 1 neighbor and he needs at least 2 to survive. This guy's dead and he'll stay dead. And this guy's alive and he stays alive because he has 2 neighbors and that's enough to survive. And that guy over there will spawn into new life because he has 3 neighbors. Now, throughout this talk, I'm going to represent cells like this, by the way. Alives are 1s, deads are 0s, and a cell highlighted in orange is the cell we're currently evaluating to decide if it should be alive or dead in the next generation. So with this background, how do we approach the Regex implementation? Well, we have a board with a bunch of cells in a certain state. I want to change some of those to make the next generation. So you could think of this as 2 separate problems. First, we need to find the cells that need to change. That is, cells that are alive that need to die, and cells that are dead that need to spawn into new life. And then we need to change them into their new state. Or you could say, replace them for a cell in the new state, right? Find the cells that need to change and replace them. Find, replace. This is now starting to sound a little bit more like a regex, right? And hopefully, that idea sounds a little less ludicrous now. Now I'm gonna add a seeded step here. We need to first represent the data in a way that's going to let us actually do this with a regex. So let's look at these 3 steps one by one. First of all, how do we represent the data so that we can operate on it with a regex? And normally in the game of life, you represent all of your cells as a 2D array of 0s and 1s, matching the rows and the columns of the board. And when you're looking at a cell, you can use plus and minus 1 offsets to find the 8 neighbors. But regular expressions don't work on 2D arrays, they work on strings. So we need to format this as a string. Imagine, if you will, a long string of 0s and 1s that sort of wraps every n characters, And that ends up giving you the same board. And in order to find the neighbors for a cell, we need to look at what's before and after in the string of the character we're evaluating. Now keep an eye on the colors. I'll always represent the neighbors before and after in green and blue. And so this is how we store the data. But now how do we find the cells that need to change? And in Regex, we can use zero with look behind and look ahead assertions to look before and after in the string of the things that we're interested in. And what these do is say, match a thing, but only if before or after the thing there's this other stuff. Now the important part is the zero with in the name. This other stuff doesn't become part of the match. It's an assertion, but it's not in the result, it's not in the match. So for any given cell, I can zero with look behind the previous 4 characters and zero with look ahead the next 4 characters, and those are my neighbors. And so if I want to match these particular cells with these sets of neighbors, I can do this, right? Match the cell that I want, that orange one, but only if what's before and after in the string meets some criteria. And if I can then replace these orange cells that I matched for the new values, I should have a game of life. Now this is worth saying again. The reason this works is that those regexes will only match one character, the one that I have to change. They match based on the surroundings, but they don't match the surroundings. So a regex replace will only replace the one character that I'm looking at. And because it's a regex applying over a whole string, it applies over the whole string at the same time, atomically. So I just need to run this replacement once, and that's going to do a whole generation for the board. And so with this idea, I should be done, right? This should do it. But there's one small issue. How do you write a regex that matches a character based on the count of characters around it that are a 1, independently of their order? And I couldn't figure that out. But at this point, I had what I thought was a reasonable chance of getting this to work. I thought this approach was sensible. And so I did what I always do, right? I was like, surely I can Google this. Surely somebody will have done this before. Apparently, though, I'm the first person dumb enough to actually try this, or at least the first one to live to tell the tale. So I can't Google my way out of this. I'm going to have to figure it out by myself. So again, the immediate problem that we have is, how do we find the cells that need to change, which is based on the neighbors, the number of neighbors around them that are 1s. So how do I find characters that, among the 8 characters before and after them, have either 2 or 3 1s? And of course, in Regex, we have the curly braces, and this lets us specify, I need X many of these. So I can say very easily, find me 2 or 3 1s before this character altogether. But what we need here is, in between the 4 characters before me and the 4 characters after me, I need between 2 and 3 1s, and I don't care where they are. And as far as I can tell, you can't do this with Regex. So this approach wasn't looking promising, and at this point I got stuck for quite a while. But then I realized this problem falls under a very specific category of problems, which is one of my favorites. And that is problems that are hard to solve, but instead of solving them, I can just cheat. Because you see, when you're looking at a cell and its neighbors, you're only looking at 9 binary digits. And 9 binary digits are not a lot of permutations. I can just brute force this. I can write out all 512 combinations of a cell and its neighbors, and then spell out what would happen in each case. And this is not exactly pretty, but I said game of life with a regex, not with an elegant regex. And importantly, we only care about combinations where the cell has to change. So I can ignore all of the combinations where it stays the same. So of those 512 possible combinations that I had, this takes us down to only 228. And obviously, writing 200 cases like this by hand is not very fun, so I wrote some Ruby code to do it for me. Now, the easiest way to brute force binary numbers in Ruby is to just count and then 2s them into base 2. Here I'm counting how many 1s are in the string to see how many neighbors we have, and then I decide whether the cell should change or not. Now, this bit looks suspiciously like game of life code, which is what we're trying to avoid. But we don't ever use this code to actually run the game. We run this once to generate the regex, and then that regex runs the game. So that's fair. And if you run this, this code will print out the 228 combinations of cells and their neighbors that represent the cell state change, either a spawn or a death. So for example, I have this combination, which is a death. I want to find the middle one to turn into a 0. So I need to search for that pattern over there. And I need to do the look ahead and look behind, so I only match the 1. And now that I have that pattern, all I would need to do is repeat it 228 times, and that should be done. But there's one more problem. Because my board doesn't really look like this thing that I have here on the left. Because I don't just have the 9 cells that I'm evaluating. I actually have a board that is much bigger than those 9 cells. So the 9 characters that I want are not all together in the string. They have this garbage in the middle, that stuff in red and pink, and I don't care about it, so I need to ignore it. Now you'll notice that this board has a width of 10, and I always have 7 of these garbage characters. So I can do this and just ignore 7 characters. Now that 7 is hard-coded. It's actually going to have to change with the board size, but we'll do that later. That's the easy bit. And now I can take this last rule, duplicate it 200 or so times, concatenate them all with a big OR, and replace that 7 with the appropriate number for the board size, and that should match all the cells that need to change. If you put that last expression in the generator code that I showed earlier, you end up generating this ridiculous file. Here you have all the combinations of zeros and ones for all the rows, all the 3 rows and all the 3 columns. And we have this code to read it. We read the lines, we put a pipe in the middle to do the OR, we replace the board size with the correct number for a board, and boom. Now we have a regex that'll match every single cell that we need to change. So this solves the find part. The only problem is, I don't know what to replace them with. Because this will find all the cells that need to change, but that is both spawns and deaths, zeros and ones. I need to know which is which. Now the good thing is, I know the cell needs to change because it matched, and there's only 2 possible values. So if it's now a 1, it needs to change to a 0, and vice versa. But the question is, what do I do here? What do I give to gsub as a parameter that is going to flip those cells? And here I'm going to have to take an intermediate step for clarity. Turns out gsub accepts a string to replace a thing with, or you can give it a block. So in this case, the regex is doing all the heavy lifting, finding me all of the cells that I have to change, and all I'm doing in the block is flipping them. And to my absolute surprise, that worked. This pattern you see here on the left, that's called a glider gun, and it's one of the things that makes the game of life magical. Here's what it should look like, and that is my garbage implementation. It actually works. And oh, and by the way, that speed, that's real time. That's how fast it goes. So it's not the fastest thing I've ever seen, but considering the horror of what I'm doing, I'm actually pretty impressed. Now, this is one way to do the thing. There's one more problem. This is not a regex. This is bullshit. I promised you, game of life with regex. Not mostly regex, but there's some sneaky Ruby in the middle. We need to do this thing with regex too. But as I said before, I needed to take that intermediate step for clarity, because so far, we've basically been doing fairly standard regex work, the kind of thing that you do day to day. But hold on to your socks, because the next bit is where it gets wild. Remember, the problem I have is that given a matched cell, I don't know whether to replace it with a 1 or a 0. And we don't yet have an obvious way of how to do this with a regex. Now, you might think that you can do this in 2 stages. Have one regex with all the combinations that have a 1 in the middle, so all the deaths, and then another one with all the zeros in the middle, all the spawns. And then you can match all the live ones that need to die, replace them for zeros, then match the others, replace them for ones, and you're done. But you can't do that. You need to do all of this in a single pass atomically, and this is partly why the regex approach is magic, because it gives me that for free. Now, to explain why that is, the standard implementation of Game of Life starts by making a new board on each generation, and then filling it based on the data of the previous generation. And that's because if you modify the board as you go, you're going to modify the neighbors of cells that you haven't evaluated yet, and that's going to modify their outcome. In this example, for example, those 3 cells highlighted in purple will die of loneliness. But the yellow one has 3 neighbors, so it will spawn new life. The board there on the right is what would happen in the next generation. But if you do this in 2 stages, first deaths, then spawns, you first kill those 3 cells, then you have no neighbors left and nothing gets spawned. This doesn't work. And obviously you have the same problem in reverse if you first do spawns and then deaths. You can't do this. So back to the problem. We match all the cells that need to change, and I need to pass something to gsub that is going to say what to change them to. That's going to resolve to a 0 for all the ones and to a 1 for all the zeros. And to explain how to do this, I need to take a little detour and talk about named captures. Now, most of you probably know that when you're matching in a regex, you can capture a chunk of the match and then use it in the replacement as a back reference. Let's say I have this phone number over here and I want to format it nicely like that. I can match the 3 different parts, capture them with those parentheses, and then replace them, making references to those 3 captures by number, 1, 2, and 3. And if your regex is super simple, this is fine. But it's common to have tons of parentheses in a regex, and that makes it really, really hard to keep track of which sets of parentheses is which capture number. And when you have that problem, you can name your captures like this. And then you can call them by name when you replace them using that \k syntax. And this makes it way easier to know what's going on. And this is what we call name captures. And you probably knew about these. But here's the bonkers part that I didn't think was going to work. First of all, you can do captures inside of your look aheads and look behinds. So you're not matching that part, you're just asserting that it's there. But if it is there, you can capture a bit and then use it later for the replacement. Now, the real bonkers bit, which I didn't think was going to work, I was just sure this wasn't going to work, is you can declare the same name for a capture multiple times in your regex. And if you have an OR, whichever side of the OR matched kind of wins, and that's the value for your capture. Now, if you go back to something closer to our regex before, we were doing something like this. This thing is going to match a 1, but only if it's preceded by 3 zeros. Now, I'm not matching the zeros, but I can capture one of them and name it. Let's name it replace. And now if that expression matched, I have a 1, I have matched the 1, but I have a capture name replaced with a 0 in it. And as I just mentioned, we can have 2 expressions with the same capture name separated by an OR. So only one of these 2 will match, and whichever one matches, that's the value of the replace capture. And I mean, this is nuts. I was 95% sure this wasn't going to work. That regex up there is going to match one of 2 things, the 1 at the end of 0001, or the 0 at the end of 1010. It matches just that final 1 or that final 0, and only if they have the prefix. But if the 1 matched, I have a replace capture that holds a 0, and if the 0 match, my capture holds a 1. You see what happened there? If I match a 0, my capture has a 1. If I match a 1, my capture has a 0. All I need to do is replace the match for the capture, and we flip the number with no code, only regex. So what we need to do now is modify those 228 cases that we had and add these captures. On any cell that is alive and needs to die, we pick a neighbor that is dead and capture that. And for cells that are dead and need to spawn into new life, we pick an alive neighbor and we capture that. We change our generator code so that it will basically go around the neighbors and pick one that has the right state and surround it with the capture. And the runner code now looks like this. I can tell each matched cell to replace itself with the capture that I chose, which happens to have the opposite digit, and now the dream is complete. I have a pure regex replace that runs the Conway game of life, which is exactly what I set out to do at the beginning. Here's our glider gun again. It still works. Now, as tempted as it is to leave it there, there's a little catch. Now, I promise it doesn't matter for where I'm ultimately going with this, but I do have to come clean. That emulation isn't perfect. Of those 228 cases that my regex needs to match, there is one, and only one, that it cannot deal with. Did you catch it already? This guy needs to die of overcrowding because he's surrounded in all directions. But I need to capture a 0 to be able to kill him, and there are no zeros around him, so I can't. This one guy won't die in my implementation. And I've tried everything, negative look aheads and look behinds, negative character classes, saying not 0 instead of saying 1, and then capturing the 0 inside the not 0, trying to capture a 0 in that interline garbage I'm ignoring. Nothing works. I need to grab it to the 0, and the 0 just isn't there. There's nothing I can grab. So as an aside, please, if you can think of any way to do this, please tell me because it's killing me. But as I said, I think this doesn't invalidate what I want to get at. So I'd like to go back to an earlier question. Why? Why am I even talking about any of this? And what I said earlier is true. I mean, this is a question that popped up in my head, and I just couldn't get rid of it until I had solved it. But there's a second side to this story, because it turns out that the game of life is Turing complete. And that's not what you'd expect for a system that is entirely defined by this one simple rule, but it is. Now, as a quick reminder of what that means and oversimplifying a bit, this means that any program you can write in any language, you can also write as a game of life pattern if you wanted to. And you can see a beautiful example here. That's the game of life running in game of life. And this is an actual full Turing machine running in game of life. And this is something I love. I love finding things that you wouldn't expect would be Turing complete. Turns out that they are. I could have an entire talk on just that. It's one of my favorite topics. So when I was thinking of this, when I was thinking whether you can run the game of life with a regex, I was thinking of that. Because if the game of life is Turing complete, and I can run it with a regex, does that mean regular expressions are Turing complete? Because that would be pretty nuts. And so I'm kind of using the game of life here as a proxy for Turing completeness, because I thought I could emulate it with a regex. And as we saw earlier, that doesn't quite work. But there's a more direct way. What if I just implemented Turing machine directly with regex? Now, as a quick reminder / intro to what Turing machines are, they're a theoretical machine that can do any computation that any other computer can do. They have an infinite tape of data, a head that can read and write that tape and that data and move the tape around, and a state machine that, given what data is in the tape and what state it's in, decides what to write in the tape, whether to move it left or right, and what state to jump to. And just this simple thing can run any program that you could write in any language. Now, to implement one of these with regex, we're going to use the same idea as before. The idea that we had in our game of life is that you can't run random logic, but in our case, we didn't need to, because we only needed to deal with a discrete set of possible patterns, those 228, because those are all the possible things I could ever find in the board. And when you have that, you can make a regex that looks for explicitly all of those cases. You look for all the possible states that your data could be in, match the one that it is in, and then modify it by capturing the little bits that you need to use in a name capture for the replacement. Now, in a Turing machine, you have the same situation, because you have a discrete number of possible states, those 8 circles, a discrete number of values that can be on the tape, and you have a discrete number of transitions between states, actions that you can take, and that's the arrows up there. So based on what state you're in and what's on the tape, you define what to do, and there's just a finite number of those. So just like before, we can do a mega regex with one clause for each possible transition, each of those arrows, matching the state that you're in and the value in the tape, and we also capture some stuff to replace values on the tape and change what state will be next, and that should do it. Now, if you remember, the problem we had before is we had a board with all the cells, and we had no control of what that board had in there, because that board is our input. So we could find ourselves in this situation where the thing that we needed to capture just wasn't there. But for the Turing machine, we can get clever and store all of the data in a format that makes sure that that won't happen. Now, to explain this, I'm going to use this example machine. What this does is it'll take a string of zeros and ones and repeat it. You end up with the same input twice. It has 8 states, those circles, and it can handle 6 input characters in the tape: 0, 1, and 4 letters that we're going to give a special meaning to. And so, just like before, let's see how we represent this data. Let's imagine that this is our tape. This has the input data in it, the string of zeros and ones between the 2 Bs. Those 2 Bs are like end markers. To run a Turing machine, we need to keep track of 3 things. First, the data on the tape, that's there. Next, we need to know where our head is. What's the tape position that we're currently reading and writing? So let's add those special hashes to do that. That first B, that's what we're reading next. And finally, we need to keep track of which state we're currently in. Let's say we're in state Q1, we'll put that in there too. And now we have all the information that we need for the state machine. We know what state we're in, where we're on tape, and what data is in the tape. Now let's say we have this transition rule. This is a sort of like Turing machine definition language that I kind of made up. And it has 2 parts separated by that slash. On the left, what condition we look for, and on the right, what to do if we find ourselves in that condition. What that one says is if we're in state Q1 and the tape has a B, write a C, move right, and change to state Q2. And so to match this transition, I need to find the head between those 2 hashes in state Q1 with a B on the tape. I can literally just search for this string, right? And then when we're replacing, if we want to move right, for example, we can capture the 1 character to the right of the tape, name it, and replace it inside the head. And then replace the character before the head with the character that we would have written in the tape. Let's say we replace the B for a C. Now we've written a C to the tape, and we move the head to the right 1 position. But we have one more problem. We need to change the state to Q2. Where does that 2 come from? We don't have that anywhere in the string. So just like in Game of Life, we can't capture it to then do the replace. And by the way, the same happens to that C that I just wrote there. Where did that come from? Now, to get around this problem, what we're going to do is we're going to make the head a lot bigger than this, like you see here. Now here we're still keeping track of what state we're in and what in the tape is reading. The head is reading just like before, but we also have all this extra crap. This is all the names for all the states that this machine can have, and also all the different input characters that you can find and write in the tape. Now if you remember, this particular machine can have 8 different states and process 6 valid input characters. That's there. If we had more states or other characters, we just put all of that in there. And we have these things just so we know that they're always there. And then we can always capture them with name captures and replace them into other parts. So for this rule down here, I can capture this character to the right of the head and put it here to move the head right. Then I need to write a C, so I capture this C right here and put it on the left of the head. And then to move to state Q2, I can capture this Q2 right here and put it where the current state goes. So what I'm doing here is I'm including all of the things that I may need to write anywhere, and I always keep them around. And that way I know that I can always capture whatever I need and change anything that I want. And this would have solved my game of life problem of not being able to find the zero to kill that cell. But I couldn't do it because I can't control what's on the game of life board. That's my input. But here, in between those two hashes, I can do whatever I want. Now, to complete the idea, this is the whole program for that state machine. These are all the transitions that you can have. And we can write a little bit of Ruby code that turns this program into another mega regex following the same idea as before. Each of these lines will turn into one clause in the giant set of ors in my regex, matching the head in that respective state with that particular character in the tape. And it'll also capture all of the right parts of the head on the tape for the replace to do its thing. That's the whole program in regex form. And you can see those captures, new left, new cursor, new right, new state, right? Those are the bits that in the next program step are going to be to the left and under the head and to the right of the head, and what state will be in next. So this whole thing looks for all of the possible contexts the head could have based on all of its possible states and all of the possible characters in the tape, and then it will replace that head and tape with the values showing the new state of the whole thing. And the code to execute this regex to the machine is what I keep promising. Nothing but that regex. And it works. Here you can see the head moving back and forth with the tape, changing the values. And once it finishes, you're going to see that the tape has the same input that we had at the beginning, but repeated twice. So we can implement a Turing machine using only regex. Now going back to my original question, does that mean regular expressions are Turing complete? And well, technically, formally, academically, very, very no. And I want to make that clear. I'm not claiming that they are, right? Like, first of all, in all the code that we saw, we had a loop around that regex. And that loop is pulling a lot of weight. Regular expressions can't loop at all, and you really need to loop if you want to do any computation. And also, it kind of depends what you mean by regular expressions. In the formal definition of regular languages, regular expressions can do all those beautiful things that we're used to doing day-to-day with the looking back and forth and the back references and the name captures. All of that is technically not a regular expression. So officially, no, they're not Turing complete. But given that with just a dumb loop around them, they can almost run a game of life, which is Turing complete, and they can absolutely run a Turing machine. They kind of are. Like, for practical purposes, the regex that you use day-to-day can absolutely emulate computation. Now, I don't think there's any actual practical purpose for this, but I also thought that was kind of mind-blowing. I did not expect to get to this answer when I started down this path. And like most weird things that I find out there, well, I just thought I'd share that with you. So I hope you enjoyed that little crazy tour, and thank you. Now, a couple of closing notes. Down here, you have the link to the repo. There's all of the code. There's a lot more comments, particularly in the Turing machine and how moving the head left and right works. I also have some Game of Life stickers if you want to have some gliders on your laptop. And I have one of the puzzles that I enjoy the most ever, which I should have at hand, but I forgot to grab it. It's over there. It's basically a regular expression crossword. And if you love regex as much as I do, you should really try this. It's going to be amazing. And yeah, we don't have time for questions, but I'm going to be around and here and then in the hallway. So please do come, grab some stickers, let's have a chat. Thank you.